In this video, we're going to do a quick recap of the titration concept. Using our handout, we'll fill in some blanks and do a couple little practice problems together, conceptual ones. We won't go quite into the math yet. That'll be in the next video. So one little correction I want to make first, though. In the last video, I was explaining this graph, and the numbers didn't really coincide with the labels properly. Number 1, 2, and 3 were fine, but 4, I had labeled it as endpoint. I didn't say that was the endpoint while I was explaining it, but I had labeled as that in the slide. So just a slight correction here. 4 is when you've gone beyond the equivalence point. So you've added too much base, for example, or too much of whatever you're adding. You've gone beyond it and you've overshot essentially at this point. The equivalence point is still number 3, like I said, and the end point has to be within the steep portion. As I was mentioning before, I just fixed that in this lesson here to show you that 0.4 on this graph is beyond the equivalence point. Okay, so just make sure you understand that. I didn't want to lead to any misconceptions with that. So let's go ahead and fill in some blanks to make sure we understand all the concepts. So the first thing we reviewed was that there's different types of acid-base reactions. You could have acid and a base that provide a salt and water. So for example, we have an acid with a base with OH, and it gives us salt and water over here. These are supposed to be arrows. And then you can also have a neutralization reaction. We have an acid and a carbonate. And so when you have an acid and a carbonate, you still get your salt. You also still get water, but you also get carbon dioxide. And that's because, remember, this is a double displacement reaction that produces one of those unstable compounds. So the H goes where the Na was, the Na goes where the Cl was, and you get your NaCl. That's your salt part. That represents that. And then you have your H2CO3 aqueous. And remember, if there's two aqueous, normally there's no reaction, except if you produce this compound here, which breaks down into your H2O and into your water. So you'd see some bubbling there. So those are the two types of neutralization reactions that we reviewed in the last video. And then we saw titration. The whole purpose of a titration is basically to use something that you know to figure out something you don't know. So this is your burette here, a piece of glassware that's precise to 2 decimal places. And it holds what's called the titrant. It's the solution of known concentration. And in your flask, you put the analyte, which is the solution of unknown concentration. And you typically put an indicator in here so color changes can happen when reactions are done. But basically, you do a reaction between your titrant and your analyte, and once it's done, you use your volumes and concentrations to figure out what the concentration of this and here must have been. So we described this curve over here called a titration curve. And so essentially what's happening is we're monitoring the pH of what's in the flask. So for example, if I start off with an acid in the flask, the pH is going to be at the start, a pH of less than 7. Because it's just a solution of H plus and Cl minus. And then notice the pH starts to rise. So the pH starts to rise because we're adding some NaOH from the burette in there, and that's because we're canceling out some of the H plus. There's some H plus swimming around in there, and so the OH and the H plus are basically coming together to make some water. We're neutralizing some of the H plus, and that's why the pH is going up. This is the pH over here just before neutralization. So we're really close to matching the H plus and the pH and the OHs together perfectly. And then we get to 0.3 here, which is our equivalence point, where the H plus and the OH, all of them in the solution, have matched each other and we're essentially neutralized. Now, acid-base reactions are quite boring. You're not going to see a color change unless you put an indicator. Now, an indicator will change color to let you know when you're close to your equivalence point. And that's called the end point. So when the indicator changes color, somewhere in this steep portion here, it should be in the steep portion, not in the curved portions, then you know that you're close to your equivalence point. Your indicator might change color slightly over here maybe, or over here, or somewhere in here. It won't exactly change at the equivalence point, but it'll be close enough because it's in the steep portion and the volume change doesn't matter that much. And then that's a good estimate of when you've reached your neutralization. You want to be within this region here when your indicator changes color. And when your indicator changes color, we call that the end point, which will be close to the equivalence point chemically, where the H plus and the OH minus have completely neutralized each other and reacted with each other. 0.4, as I mentioned, that's beyond the equivalence point. So you've overshot, you put too much base in there, and now your estimate's probably off, or too far off, and you're going to overestimate your concentration of your acid that was there. Because you're basically saying, I needed way more base to neutralize it. Did you? Not really. You just put too much and you didn't stop on time. Now this is the a titration for a strong acid and a strong base. I know that because the equivalence point is at 7. The pH of 7 means you had a strong acid and a strong base being titrated, and that varies for strong acid, weak base, strong base, weak acid. So it varies, and that you can see in the first video. We then saw the steps that were used to do a titration. So generally what you want to do is you're going to fill your flask with your solution of unknown concentration. So let's say it's your acid. Usually you want to use a volumetric pipette for that because you want to get some precise measurements there. You're going to add some indicator, a few drops of indicator, 2 or 3 drops, because eventually when the reaction's done, you want to see a color change. You're going to fill your burette with the titrant, the thing that have known concentration, and you're going to make a note of where the initial volume is. And basically you're going to add drop by drop by drop by drop until you get a nice persistent color change, and you're going to make a note of your final volume. Now, I'm not going to worry about decimal places right now, but let's say I started off over here. Let's say the level was at 2, and over here we were at 24. That means I did 24 minus 2. I put 22 mils of the base in to neutralize or to get close to my equivalence point. I would do this 3 times. I would basically do 3 trials and then take an average of all of them. And that average is what I would use in future calculations to predict what the concentration would be. So this is what a table looks like for a titration. Your title is Table 1, titration of 20 mils of H2SO3. This is the concentration you don't know. So you'd put how much you're titrating and what you're titrating, and with what you're titrating it with. So with the known concentration of NaOH. And you would write a title exactly like this. You would have your trial 1, 2, and 3. You would have your initial burette reading where you're starting, your final, and then your volume of NaOH used in the end. So here's an example. This is the same burette, just kind of side-by-side pictures at different parts of the burette. This would be our initial here. So we have 2, 2.1, 2.2, about 2.20, because you get 2 decimal places. So initial burette is 2.20. That's in milliliters. And our final is about 22, 22.1, 0.2, 0.3, 0.4, 0.5. About 25, 22.50. So 22.50. The readings go up as you go down the burette because you want to be able to subtract in this way. But basically, to find your volume of NaOH here, you do your 22.50 minus 2.20, and that would give you your volume of NaOH used. So about 20.30, because we get 2 decimal places when we use a burette, which is quite precise. And then we would do that essentially 2 more times, and you could take an average of all those volumes there, and that would be the volume required to neutralize your acid. So we saw that when you do a titration, your endpoint should be the lighter color change, for example, especially in this situation here, because here's your equivalence point, and we start to change color in this region. So when you first change color, you're really close to your equivalence point. If you go beyond, you might have gone too far. We don't know. So a dark pink, this is too far. You got to go drop by drop and slow down when you get close to your equivalence point. So that's what we studied in the previous video. This is just a recap, filling in the blanks to make sure we understand the concepts. Do make sure you can practice choosing indicators, which you saw in the previous video as well. And also practice understanding when you have a strong acid, strong base, weak acid, or strong acid, weak base titration based on the equivalence points. Make sure you watch the videos that go over the demonstration of a titration. You should be able to label a figure like this and draw a figure like this based on your titrations that you're doing. In the next video, we're going to do some calculation problems for titration, and we'll do some sketching. So sketching is really important to make sure you understand the concepts.